Hi everyone, in 2.3 we'll look at the speed of mechanical waves. So this is the speed at which the waves propagate through the medium. And in general, for mechanical waves, the speed is given by the square root of some measure of the restoring force, which will bring particles back towards equilibrium, over a measure of the inertia of these particles resisting that pull back towards equilibrium. So specifically for a wave on a string, the speed will be the root of Ft over mu. Ft is the tension in the string in newtons, which we'll look at cases where this is constant throughout the string. And then mu is called the linear mass density. This is the mass per unit length for the string. It's m over L, so that's mass in kilograms over length in meters. And this will give us the speed of the waves throughout the string. So here, the tension is a measure of that restoring force that pulls the particles back to equilibrium. And notice that the wave speed depends on the square root of tension. So as the tension in the string increases, the wave speed also increases. Then we have the speed inversely proportional to the linear mass density. So strings with a higher linear mass density would have a lower wave speed throughout that string. Okay, let's try some examples.
Example 6, a string of length 1.2 meters and mass 50 grams is connected to a wall and to a mass connected to a pulley as shown. When the string is plucked at one end, the pulse travels to the other end in 50 milliseconds. What is the value of the mass? How would the travel time change if the mass was doubled? Okay, so we can use the length of the string and the time the pulse takes to travel from one end to the other in order to find the wave speed. So we'll have v equals d over t, delta t, since it's a constant speed. So that's 1.2 meters over 50 milliseconds, 0.050 seconds, which gives 24 meters per second for the wave speed. Then mu we can find as well is m over L, mass per unit length. So 50 grams, 0.050 kilograms, over 1.2 meters, which is 0.0417 kilograms per meter. Now this mass is what we're looking for, and this mass creates the tension in the string. So we have tension here, and then the weight, and they will be equal because of Newton's first law since it's at rest. So we'll have Ft equals Fg, which is that suspended mass times g. And for now we're looking at cases where the tension is the same throughout the string. So let's use the equation for wave speed on a string, v equals root Ft over mu, in order to solve for this suspended mass. So we have v squared equals Ft over mu, or mg over mu. So solving for m, we have mu v squared over g. So the mass is 0.0417 kilograms per meter times 24 meters per second squared over 9.8 meters per second squared, 2.45 kilograms. Move that up for a second. Okay, the next question is, how would the travel time change if the mass was doubled? So if the mass was doubled, well, looking at this equation here, if I just plug in root mg over mu, we can see that the speed is proportional to the root of the mass if all other factors are constant. So v is proportional to the root of m. So this means that v would increase, the speed would increase by root 2 if we were going to double the mass. Now let's look at how the time changes when the speed changes. So delta t equals d over v. So delta t, time, is proportional to 1 over the speed. So that means that if v is increasing by root 2, the time is going to decrease by root 2. That's that's really sufficient, but we can find exactly how much it increases by then. We can take 50 milliseconds and divide by root 2, which is 35.4 milliseconds. Example 7, a wave on a string is described by y at x and t equals 0.02 meters sine 12.57 radians per meter x minus 638 radians per second t plus 2.34 radians. The linear mass of the string is 5 grams per meter. A, determine the wave speed, and B, determine the tension in the string. Okay, so I've written out the wave equation here, and we know that in front of the x we have k, and then here we have omega. And I've shown you how we can use v equals omega over k to find the wave speed. 638 over 12.57 gives 50.76 meters per second. Then with that we can find the tension, since we know v equals root ft over mu. So ft will be v squared mu, which is 50.75 meters per second squared times 0.005 kilograms per meter. So we do need to convert that to get newtons. And then I have 12.9 newtons for the tension in the string. Example 8, a steel wire of length 30 meters and a copper wire of length 20 meters, both with diameters of 2 millimeters, are connected end to end and stretched to a tension of 150 newtons. During what interval will a transverse wave travel the entire length of the two wires? The density of copper is 8,920 kilograms per meter cubed, and that of steel is 7,860 kilograms per meter cubed. Alright, so I've drawn this and written out the information. So we have the length of each piece of wire and its density. The radius is 1 millimeter, half of the diameter, and then tension throughout the entire wire is 150 newtons. So we're going to need to find mu, the wave speed, and then the time it takes for the wave to pass through each section. So I've divided my page so we can do it for steel and copper kind of in parallel. Okay, so we want to use mu equals m over L. We don't have the mass, instead we have the density and the dimensions. So we can plug in for mass density times volume over length, which is density times area times length over length, and that will cancel. So we'll have density times the area, the cross-sectional area, which is pi r squared. Okay, so when I find mu here, I have the mu for steel will be 7,860 kilograms per meter cubed, pi, and then 1 times 10 to the negative 3 meters squared, which is 0.02469 kilograms per meter. And then I'll just repeat that here for copper, 8,920 kilograms per meter cubed, pi, 1 times 10 to the negative 3 meters squared. And for copper, that's 0.02802 kilograms per meter. Okay, and now let's do the wave speed. I've just added this in. So we want v equals root ft over mu, 150 newtons over 0.02469 kilograms per meter for steel, gives 77.9 meters per second, and for copper, 150 newtons over 8,920 kilograms per meter cubed gives 73.2 meters per second for the speed of the wave in copper. Okay, and now with that we can find the time. So we'll do the time in steel first. Time is going to be the distance over the speed. So that's 30 meters in the steel over 77.9 meters per second, which is 0.385 seconds. And the time in the copper will be 20 meters over 73.2 meters per second, so 0.273 seconds. And that's really done. Now we can add up to get our total time. 0.385 seconds plus 0.273 seconds gives 0.658 seconds for the time it takes the wave to travel through both pieces of the wire.